talk about water and aqueous solutions. So, we're going to do just a really brief coverage of water and some of its properties and what makes water so special. And then we're going to start talking about aqueous solutions. So, scientists have to figure out the concentration of solutions for different reactions because they want to know how many moles or how much of each substance is in a solution. Or maybe when you're at the doctor and someone's hanging an IV, if someone's hanging an IV, they need to make sure that there's the correct amount of whatever medication you're supposed to be taking in that solution that's in the IV drip. So, some of the basics of water. Water is a bent structure, okay? And so, if you look up here, you can see that water has this structure, and that structure is it's got this 104.5 degree angle. Okay. And there are some other things that you can look at in this structure, that this diagram that I have here. So we know from electronegativity, the electrons get pulled towards oxygen and away from hydrogen. There still is that chemical bond there, but the electron cloud is more concentrated around oxygen. And so that creates this partial negative charge right here. And then we have a partial positive charge here because the electron cloud has shifted away from the hydrogen. So with that bent structure, okay, and also with that partial positive and partial negative, what happens is you have hydrogen bonding. So if you look at this diagram over here on the left, you can see that there's this really strong attraction between the partial positives on hydrogen and the partial negatives on oxygen. Okay. And so you end up having hydrogen bonding. And so this allows water to have a lot of its properties. Water is known as a universal solvent. It is really good at dissolving a lot of things. Water is polar. So water dissolves polar things. Water also is going to dissolve ionic compounds. Water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. That's a very high range for something that has a molar mass that's so small. So if we remember, the molar mass of water is 18.02 grams per mole. And so you would expect something with 18.02 grams per mole molar mass to boil at a much lower temperature. But it doesn't, and it doesn't because of these attractive forces of the hydrogen bonding. And again, that structure of water really causes that strong hydrogen bonding. Water is considered to have a high specific heat capacity, which means that it takes a lot of energy to raise the temperature of water. So water has a specific heat capacity of 1 calorie per gram degree Celsius, or 4.18 joules per gram degree Celsius. And you might remember we've talked about this previously, but that's why, like, when you run at the beach, say you forget your sandals and you're running across the sand and it's super hot, and then you jump into the water and it's really cold. It's the same temperature outside, but it takes a whole lot more energy to heat up the water per gram than it does to heat up the sand per gram. So why does water beat up? Well, remember in our last diagram, we had the hydrogen bonding. So the hydrogen bonding, those attractive forces, causes water to pull in on itself. The inward force minimizes the surface area. And so what happens is you end up having a really high surface tension for water. There are actually little insects that can walk on water, and they can walk on water because of this high surface tension. A way that you can kind of visualize the surface tension, if you walk outside in the morning and you see the dew on grass, or say you just waxed your car and you see the beads of water on your car, those beads of water, they form rather than the water flattening out, they form because of that high surface tension on water. The surface tension can be broken down, though. It can be broken down with a surfactant or a detergent. So if you think about two things that don't mix very well, oil and water, when was the last time you cleaned the dishes at home? Well, what if you cooked with butter or oil? That pan that you used is really hard to get clean. But as soon as you pour soap on that pan and then put water on it. Now, all of a sudden, you can break down the two things that are usually immiscible, that aren't going to mix well together. Because what happens is the detergent breaks down the surface tension of the water and allows those two, the oil and the water, to mix. So, phase changes of water. Again, we just talked about this, but we would expect water to actually be a gas at room temperature. But water has a really high heat of vaporization. And the reason for that high heat of vaporization is because your water molecules are holding on to each other because of those hydrogen bonds. So, molecules with lower molar masses are most often gases, but water has a low molar mass, remember 18.02 grams per mole, but it is a liquid at room temperature because of hydrogen bonding. So hydrogen bonding is responsible for the lower density of ice than that of water. And the reason that it's responsible is because what happens is the hydrogen bonds cause the water molecules to kind of puff out and to form kind of this hexagonal kind of crystal type structure. And so as those water molecules get farther away from each other, that's what causes a higher volume. That higher volume at the same mass gives it a lower density. So ice floats on its liquid form of water because it has a lower density. And remember, less dense things float. Now, remember, we just talked about water, and water is a universal solvent. So in many cases that we're going to look at, we're looking at water as being our solvent. So what is a solvent? A solvent is what is doing the dissolving, and a solute is what is being dissolved. Now, your solvent does not always have to be liquid, and your solute does not always have to be a solid. Your solvent and solute can be solid, liquid, or gas. So, for example, you could have carbon dioxide is your solute dissolved in water, and that is going to give you your carbonated beverages. So, your solute and solvent can be solid, liquid, or a gas. The solvent is what is doing the dissolving, what is in the greatest amount, and the solute is what is being dissolved. And the solvent-solute combination causes something to be a solution. A solution is a mixture of two or more substances that is uniform throughout. And this is a homogeneous mixture, you might remember from our previous discussions. So what we want to do is we want to look at the concentration of solutions. The concentration of a solution is the amount of solute in a specific amount of solvent. And often we measure this in molarity, but there are lots of different ways that we can measure concentration. And we can discuss concentration by saying something is concentrated or something is dilute, okay? And what do those things mean? So that's what we're going to look at for the rest of this discussion. So solubility. When we're looking at solubility, we need to understand that things dissolve because of the attractions between the particles of the solute and the water or the solvent, whatever the solvent is. The molecules the attraction is great enough to overcome any attractions between the solute particles. So if you look at this diagram right here, this is indicating a sodium chloride crystal has been broken up. And the reason it's being broken up is because these partial positives on my water are going to be attracted to the partial negative from my chloride. And then the partial negatives on the water are going to be attracted to the partial positives. So now that attraction between the sodium ion and the chloride ion is not strong enough to fight the attraction or the attractive forces with the water molecules, okay? And so the attractive forces now between the sodium ion and the partial negatives of the oxygen is stronger than the attractive forces between the sodium ion and the chloride ion. And so that's what causes something to be dissolved. Things become soluble or are soluble when the attractive forces between the solute and solvent particles become stronger than the attractive forces between the solute particles themselves. So solubility. When two liquids are not soluble, they don't mix, they're called immiscible. And the best way to look at this would be like oil and water or oil and vinegar. If you've ever gone to an Italian food restaurant that serves you with like some oil and balsamic vinegar and you mix the two of them on a plate, they don't ever mix. And the reason they don't mix is because they're immiscible. They don't mix, and because they're not soluble within each other. But we can look at solubility in a couple of different ways, or types of solutions in 3 different ways. When we're looking at a solution, we can call that a saturated solution, an unsaturated solution, or a supersaturated solution. And the examples that I can think of, my favorite example to use is something like sweet tea. Okay. When you have sweet tea is made by increasing the temperature of that tea super hot and dissolving that sugar in it. You dissolve way more sugar in sweet tea than you would be able to at room temperature of the tea at room temperature. That is a supersaturated solution. A supersaturated solution contains way more solute than should be dissolved in the solvent. Now, an unsaturated solution would be like you've got your tea and you don't have any sugar, or you ask for sugar and someone's like, oh, here are a couple of crystals of sugar. That's going to be unsaturated. You can still add more sugar and it will still dissolve. Now, a saturated solution is when you've gotten to the point where the solution has a maximum amount of solute for a certain amount of solvent. So in this case, it's like you've added just enough sugar to where no more sugar will dissolve at your cold iced tea temperature. Okay. So unsaturated, you can still add more. Saturated means that you have exactly what you can dissolve. And then supersaturated contains more solute than you should be able to dissolve. And the only way for us to make a super saturated solution is by changing the temperature or changing the conditions to get that solute to dissolve, and then bringing it back very slowly, ever so slightly, back to room temperature. So what are some factors that affect solubility? First, surface area. If I have something that I want to dissolve, so say I wanted to dissolve some sugar, and I've got sugar cubes and I've got powdered sugar and I've got sugared crystals. Well, your powdered sugar is actually going to dissolve faster. And the reason for that is because the particle sizes are smaller. So you have to think about it. If I grind something up, if I crush something up and then try to dissolve it, it's more likely to dissolve because I have more surface area in contact with the solvent particles. So as I increase the surface area, and I increase surface area by making the particles smaller, because by making the particles smaller, I've now increased the amount of surface that is in contact with your solvent. That is going to allow solubility to happen faster, or allow dissolving to happen faster. Agitation. When was the last time you mixed like a drink mix into a water bottle? So what do? Well, you pour your drink mix into the water bottle, you cap the water bottle, and you shake it, right? You shake it. And then that's going to cause that sugar packet, whether it's your Kool-Aid packet, your Crystal Light packet, whatever it is, that's going to cause the solution to form faster, or the dissolution to happen faster. It's going to cause your sugar crystals to dissolve at a faster rate. Another thing is heating, and we just talked about this in the last slide. If I heat my tea, then I can dissolve more sugar than if I didn't heat it. So when I'm heating it, though, remember when we talked about heat and energy, we talked about how particles are moving faster. So if particles are moving faster, they're colliding more often, and so therefore they're dissolving things better. So heating causes particle collisions to happen faster, and so therefore it allows things to dissolve better. So pressure is only going to increase the solubility of a gas. So it is really important that you see that this is for a gas only. Okay. And we can use Henry's law. Henry's law says the solubility at one condition divided by the pressure at that same one condition is equal to the solubility of the second condition at the pressure divided by the pressure of that condition. So in this case, we have the solubility of gas in water is 0.77 grams per liter at 3.5 ATM. So 0.77 grams per liter at 3.5 ATM. What is the solubility? So we're looking for the solubility at 1.0 ATM. So what you would do is you would do your 7.7 grams per liter divided by 3.5, and that's going to end up giving you 0.22 grams per liter. And that makes sense because what's happened is I've dropped the pressure, so less is going to be soluble in that situation. So now let's talk about concentrations, and this is where the math comes in with solubility in solutions. So you can talk about concentration two different ways. Qualitatively, so you can say, oh, this is a dilute solution, or this is a concentrated solution. So the example that I typically use in class is like if you're going to give a kid apple juice or orange juice, oftentimes with a little kid, you're going to dilute that solution. So you're going to add water to make it more dilute. It's going to be less concentrated. Okay. Or you can even like go to the store and you get that super concentrated fruit punch mix and you add water to it to make it drinkable. The concentrated solution is what you have before you've added the water. You dilute it to make it drinkable. Okay. Or quantitatively, we could look at it in terms of molarity, which is symbolized by capital M, molality, which is symbolized by an italicized lowercase m, parts per million, which we use parts per million all of the time. You just don't realize that you use parts per million, but the water district that's distributing water to your home, they use parts per million because they have certain particulates that are dissolved in your water, but they can only have a certain concentration. And that concentration is determined by the parts per million. So maybe parts per million of chloride in the water, or parts per million of the fluoride in your water. Some water districts treat water with fluoride for your teeth. Okay. Percent by mass is another one. Percent by volume or grams per liter. And we're going to look at all of those. So before we get started, please make sure that you pause this and get this table. So I gave you a printable of this, and you're going to fill in your information in this space. So I have filled in the table, except for this is where you're going to do all of your work for the remainder of this presentation. So please make sure that you have that accessible. So let's take a look at molarity, okay? Molarity is measured in moles of substance divided by liters of solution. Molarity equals moles of substance divided by liters of solution. So our question is, what is the molar concentration of a 3-liter solution with 52.5 grams of NaOH dissolved? So this diagram up at the top here shows how you would make your molar solution. So in this case, we have 3 moles per liter solution. Okay. That's not what this example is, but just the diagram. So in this case, what we do is we put our solute on the bottom, we find the mass of that, and then we add water up to, there's usually a line right here, and you add water to that line where the meniscus is at that measuring point. And so this is called a volumetric flask, and this is how you would make a solution, okay? Your standard solution in a chemistry lab. So when we look at this question, we need to organize our information that's given to us in our question, okay? And so we want to see, what is the molar concentration? I'm trying to find molar concentration of a 3-liter solution. So 3 liters, that's going to be my volume or my liters. Okay. And then I have 52.5 grams of sodium hydroxide. So here, notice I'm given grams. Okay. Whenever I have grams, I always want to go to moles in a situation like this. Okay, so our first step is going to be to convert to moles. So I have 52.5 grams of sodium hydroxide times 1 mole divided by 44.00, and that's the molar mass of sodium hydroxide. And that's going to give me a mass of 1.3 or moles of 1.3125 moles of sodium hydroxide. Then I'm going to plug that into my equation, molarity. Remember, if I write that up here, molarity equals moles of solute divided by liters of solution. Okay, so when I go ahead and plug that in, I get 1.3125 moles per 3 liters. That gives me 0.438 molar. And then you would box your answer here. Okay. Your next question is also a molarity question, but now I'm asking you how many moles of sodium hydroxide are contained in 65 milliliters of 2.20 molar solution. So my question is how many moles? That's what my question is. Okay, I am given my volume, okay, and I'm given my molarity. I'm given my volume in milliliters. To go from milliliters to liters, you are going to divide by 1,000, okay? So you need to convert that to liters. So look at our equation. Molarity equals moles of solute divided by liters of solution. So now I need to manipulate that. Molarity times volume equals moles. Molarity times volume equals moles. And if you look at this from dimensional analysis, molarity, the units for molarity is moles per liter times volume in liters. That's going to end up canceling liters. You're going to end up getting moles. So that's what you need to do in this question. So I do 2.20 times 0.0650 liters. So remember, I converted my milliliters to liters by dividing by 1,000. That gives me 0.143 moles. And I want to always answer my question in the correct number of significant figures. In my question, my given, I have 3 significant figures. In my answer, I end up having 3 significant figures. So sometimes scientists want to dilute things. How would I obtain a 0.1 molar CuSO4 solution or copper 2 sulfate solution from my 25 milliliters of 0.2 molar CuSO4? So your equation that you're going to actually use is you're going to end up using your dilution equation, which is M1V1 equals M2V2. Okay, so you want to obtain a 0.1 molar. So that's going to end up being my M2 from my 25 milliliters. That's going to be my V1 of 0.2 molar solution. So that's going to be my M1. And I'm going to go ahead and plug that in to solve for my V2 because I'm really being asked, what is my final volume going to be? My final volume is going to be M1 V1 over M2. So I look at that and go, okay, 0.2 molar solution times 25 milliliters. And I can keep my 25 milliliters because then that will just allow me to answer in terms of milliliters, divided by 0.1 molar. Because notice my molarity cancels or my molar cancels. So 0.2 divided by 0.1 is 2 times 25. So I am going to need to dilute to a volume of 50 milliliters by adding 25 milliliters of water. So now we're going to talk about molality. Molality is moles of solute divided by kilograms of solvent. So your question is, how many kilograms of H2O of water must be added to 75.5 grams of calcium nitrate to form a 0.500 molal solution? So I'm going to underline the things that I have. I have my molality. I have 75.5 grams of solute, and I'm wondering how many kilograms of water. Okay, so I'm looking for this value right here, my kilograms of solvent. The very first thing that I'm going to do is I'm going to convert grams to moles. I find the molar mass of calcium nitrate by finding the mass of 1 calcium, 2 nitrogens, and 6 oxygens. That gives me a mass of 164.10 grams. So I do my molar mass conversion by going from grams to moles. 1 mole goes on top, grams goes on the bottom. Grams end up canceling. I get 0.460 moles. Okay, that's how many moles I have, but I still need to go back to my question. And my question is asking me how many kilograms of water. So how did I get that? I have my molality equals moles of substance divided by kilograms of solvent. And in this case, it's water. So if I cross multiply, I get molality times kilograms of solvent is equal to my moles. So if I divide both sides by molality, I'm going to end up getting kilograms of solvent. And that's how I figured this out. Another way to look at it is moles cancel and kilograms kicks up onto the top because it's 1 divided by kilograms on the denominator. So I end up getting 0.920 kilograms of water. So now we're going to look at grams per liter. Grams per liter is exactly what it sounds like. So it should be an easier equation. I believe that molarity and molality are the more challenging ones here. But in this case, grams per liter, it says what mass of AgNO3 can be dissolved in 250 milliliters of solution if the solubility is 2.22 times 10 to the 2 grams per liter. So 222 grams per liter. So I have the solubility. So I have my grams per liter and I have my liters of solution. I'm just going to remember divide by 1,000 to get liters. And I'm trying to solve for grams of solute. Okay. So in that solving, I'm going to do, I have my 222 grams per liter equals X divided by 0.250. And looking at this, I end up getting my grams of solute equals 222 times 0.250. So that gives me a mass of 55.5 grams of silver nitrate. Next up is parts per million. So parts per million is very helpful if you ever choose to go and work for a local water district. We're going to look at the parts per million of a solution. So the question says calculate parts per million. And remember, million is 1 times 10 to the 6. Remember that for a second. So we're looking at parts per million of a solution made with 0.57 grams of PbNO3, so that's going to be lead nitrate, in 6,552 grams of water. So the first thing that you're going to do is you have parts per million equals grams of solute divided by grams of solution times 1 times 10 to the 6. So remember, I said parts per million, and per million is 1 times 10 to the 6. So that's where we get the 1 times 10 to the 6 right here. And really, we're looking at it in the part divided by the whole. The grams of the solute divided by the grams of the solution. Well, my grams of my solute is 0.057 grams, and my grams of my solution is 6,552 plus the 0.057 grams. So let's go ahead and plug those numbers in. We get 0.057 grams divided by 6,552.057 grams. Now, if you're wondering where I got that number, this is my mass of my water plus the mass of my solvent, because that's what makes up my solution, the mass of my solution. And then times 1 times 10 to the 6, I get 8.7 parts per million. Okay. Now, looking at mass percent, if you remember when we've talked about mass or talked about percentage, percentage is a part divided by a whole times 100. Percent per 100. Okay. Calculate the grams of solute required to make 2,500 grams of a 0.90% solution. So, percent solution, percent mass divided by mass. It's the part divided by the whole, the mass of the solute divided by mass of solution. And if this looks familiar, it should. It is exactly what we just did, mass of solute divided by mass of solution. But instead of saying parts per million, we're basically looking at parts per 100 or times 100 or your parts per percent, okay, percent. So here we look at this and we have 0.90. We have to turn that into the decimal. So divided by 100 and then times the mass of the solution. And we have been told in our question, our solution is 2,500 grams. So then finding that, we calculate out to be 23 grams of sodium chloride are needed. And then we have our percent by volume, and this is our last one. Percent by volume is the volume of the solute divided by volume of solution times 100. And again, if this looks familiar, it should, because instead of using mass like we did in mass percent, we're using volume in volume percent or percent by volume. Okay, so what is the concentration in percent V over V, or the percent volume of a solution with 25 milliliters of ethanol diluted with water to a total volume? So total volume is our volume of our solution of 275 milliliters. Now, it's worth pointing out we would use percent by volume when we're dissolving a liquid into another liquid. So our solute is our liquid ethanol in this case. So we're going to find the percent. We have 25 milliliters of solute divided by 275 milliliters of solvent, or sorry, of solution, times 100 gives me a 9.1% volume. So one last thing I wanted to talk to you about is electrolytes. Electrolytes, when we're looking at solutions, our solute is what's being dissolved. Our solution or our solvent is what is doing the dissolving. Aqueous solutions are where water is your solvent. Okay. And solvation is when a solute is dissolved in a solvent. And that's when your solvent particles surround your water, solvation is when a solute dissolves in a solvent. So that's when your water molecules are going to surround your solute particles. Now, when you have an ionic compound, they dissociate in water. So when I have something like NaCl, solid, and it dissolves in water, what ends up happening is I end up having Na plus aqueous plus Cl minus aqueous. And that's actually what allows your ionic compounds to conduct electricity when dissolved in water, because these ions dissociate and it allows for your electricity to flow. Now, electrolytes, going back to that electricity, electrolytes are compounds that conduct an electric current in aqueous solutions. So ionic compounds are electrolytes because they're going to conduct electricity when they are dissolved in water, when they're in aqueous solution or in molten state. Now, we have two different types of electrolytes. We have strong electrolytes and weak electrolytes. Strong electrolytes are ones that dissociate completely. They break down completely into their ions, whereas weak electrolytes, they do not break down completely. So there is still some of the solid that is left unionized, or it's not going to break down into its ions. So you'll notice that in some of your questions for your assignments this week, is what is an electrolyte? An electrolyte is something that when dissolved, it's going to conduct electricity, or when it's in its molten or melted state. Strong electrolytes completely dissociate or break down into their ions, whereas weak electrolytes, there's still some left unionized, so they don't conduct electricity as well.